Hello everyone, welcome to the presentation of our paper titled Urban Tree Generator, Spatio-Temporal and Generative Deep Learning for Urban Tree Localization and Modeling. In short, in this paper we present a new computer vision and deep learning based approach to perform tree counting and localization in urban settings. We solved primarily two challenges in this work. First, city-scale tree or vegetation localization needs manual work or high user intervention and therefore is costly and slow. Secondly, classical approaches like index-based thresholding is not robust across cities. In this work, we used satellite snapshots of a city across time as input. Then we answered the following questions. Given any city in the world, what are the areas of vegetation, the tree cover percentage, the count of trees, and the location of all the trees? Lastly, we presented a comprehensive analysis over 4 test cities, namely Chicago, Indianapolis, Austin, Texas, and Lagos in Nigeria, and found accuracy in the 87 to 97% range. We showed that our approach outperforms state-of-the-art counting models in this context. Furthermore, the knowledge learned in our models can be transferred from one city to another. We start with 12 months of satellite imagery vertically stacked and run them through our segmentation model to get 3 classes: tree, graph, and everything else. Then we use additionally freely available road and building footprints alongside with the results of the segmentation to cluster the tree segments into one of 4 clusters, which are residential, industrial, roadside, and park. Then, for each configuration, we train and use a conditional GAN to generatively produce tree locations and place them on the map. Though the locations are outputted as a probabilistic distribution of trees, we discretize them to get point locations, which allows us to evaluate against ground truth that are both hand-labeled and governmentally vetted data. We claim the following contributions: segmentation, clustering, tree location estimation, scalability, and a segmentation dataset, which we have made available for all, linked in the paper. Now let us look at the observations we made to establish the work. The first observation we had is the fact that greenness in cities varies over time. This can be seen in the figure here, where we have plotted NDVI, which is likely the most popular vegetation index, indicating greenness or chlorophyll reflectance. The sine curve-like nature establishes this intuitive observation for all 4 cities, though the patterns may vary. Secondly, we cannot assume that very high-resolution aerial or point cloud data like LiDAR is available for all cities in the world. Lastly, in cities, trees and vegetation are usually managed under some authority, which results in some uniform rules in certain configurations that we aim to capture as patterns. We call these procedural rules in our paper. Here we show some illustrations to motivate why we use the 12-month temporal approach instead of a single snapshot of a city. We show using June data that there is an underestimation of trees, using September data there is an overestimation, and using December data there is high underestimation. However, when using 12 months of data, we get the most accurate picture of vegetation cover over Austin, Texas. It is also quantified as F1 scores, as was shown. Here, the holistic view is shown to justify why 12 months data is used in our segmentation model for all cities, giving us the highest F1 scores. Now, let us look at the pipeline or methodology in detail. The pipeline can be separated into 2 high-level parts. First, segmentation, and then the tree location estimation or localization. First, let me hone in on segmentation. We start off with 12 satellite snapshots of a city. These satellite snapshots are taken at 1-month intervals using PlanetScope 3 meters per pixel data daily captures. Then they are stacked vertically. We note that each snapshot has 4 channels, namely red, green, blue, and near infrared. Therefore, for 12 such snapshots, for every city, we get 12 multiplied by 4 equals 48 dimensional matrices to segment. Next, we use minimal labeling for each city. We showed in the paper that only 10 to 15% labeling is enough for optimal performance. Next, we use a modified UNet network which can segment the 48-dimensional data into three classes that are trees, grass, and everything else. The model's architecture and codes have been made available in our paper. From the network, we consequently get these three classes of segments as output. Next, these segments go through a clustering engine to further classify themselves into several configurations, such as residential, industrial, roadside, and park configurations. Now we focus on the second part of the pipeline, which is localization or tree location estimation. In this step, we take the outputs of the previous step as input. Recall that the output of the previous step was 4 configurations of the segments. In this step, we train one conditional generative adversarial network or conditional GAN for each configuration. To train such a network, we input hundreds of thousands of synthetic data for each cluster and use Gaussian heat maps of the tree locations as target outputs. I will elaborate this in the coming slides. But after training and calibration, once real-world data is processed, we get precise tree locations as shown on the right. As noted previously, we call the uniform patterns of tree locations procedural rules. We have 20 such procedural rules in our system governing the GANs. Here, the common equation for the rules are shown. For brevity, I will discuss one of them in the presentation. Let us walk through the rule governing roadside Chicago, that is the rule set that governs and optimizes roadside configurations of Chicago. Before going forward, let me state that U here stands for universal or trivial rules, such as no tree will overlap a building or a road or another tree. As for cluster-specific rules, these rules govern the distribution of the trees in two parts of the segment. One is the boundary and the other is what we call inner. Boundary is given as twice the diameter of the field of neighborhood of a tree around the corners of a segment as shown with dashed lines in the figures. As you can see, these distributions are different for different configurations which we extracted from heuristics of real-world labeled data. Specifically, we can see that for roadside cluster, most of the trees are localized around the boundary. That said, it leads us to a question: where to put how many trees? This is resolved by our GAN network calibration and training. The training of our conditional GANs are done using synthetic data that inherits the procedural rules. As there is no one-to-one mapping between the input and output counts in a generative process, we trained multiple conditional GANs to get the counts to see which gives us the highest accuracy. We kept a fixed size of a 80 square meters tile and varied the number of trees in training and then recorded the accuracies as shown on the plot on the left. Then we used the GAN resulting in the closest to ground truth density for a given procedural rule. On the right, we show the output of one tile of the roadside Chicago rule where the yellow circles are trees and the blue segments are tree segments from the previous step. Now for completeness, let us walk through how the synthetic data is created. First, trees are randomly placed, adhering to only universal rules. We use Chicago as an example. Then the trees are clustered into different configurations. Next, we only keep the segments and remove the trees. Then we synthetically place the trees adhering to the optimized rules learned from heuristics inside the segments. At this point, we are ready for training the GANs. The segments serve as inputs, whereas the trees, represented as Gaussian heat maps, serve as the target outputs of the GANs. As such, the conditional GANs are trained. In this slide, we justify why we used SSIM as our distance metric in evaluation and also loss function among other distance metrics. We see that on the right, as the predicted tree heat map moves away from the ground truth, SSIM exhibits a natural decay on the plot on the left. This is more desirable from the other metrics that we compared against. Now, putting it all together, we see a subjective example beside a ground truth aerial snapshot to establish the accuracy of the localization. It also highlights the low quality of data on the left, which we used as input, but was still able to extract the locations with high accuracy and precision. Now, let's look at how well we did. Here, we show examples from each configuration beside ground truth aerial data where it was available to show subjective accuracy of our approach. In this slide, we show several ablation studies where it is shown that as the rules are progressively removed, the performances become worse. It can also be used to rank the impact of the rules. We also see very high accuracy of tree counts with all rules activated. For brevity, we show one example inside US and another outside. All 4 cities are shown in the paper. These are the line plots showing the ablation study shown in the last slide. Here we show the performance of our system benchmarked against other literature and governmental data. As ground truth for tree segmentation in US cities, we use National Land Cover Database, and for Lagos, we use data from United Nations Food and Agriculture Organization. We see that we get very close to ground truth in segmentation in the top table. As for tree counts, we see that we get above 93% accuracy in most of the test cities and its subsets relative to a varied number of ground sources in the table in the bottom. Here we show the performance of our approach outperforms most of the state-of-the-art counting networks from recent deep learning frameworks in this context. Now let's look at knowledge transferability. Here we show that our system is robust and exhibits knowledge transferability. For example, if we use our method trained on Chicago and process Austin data through it, we still end up with segmentation accuracy above 70% and count accuracy above 89%. This holds true for other combinations as well, as shown in the tables. To recap, another subjective example is shown. We have made our annotated data and code available for all, and the link is available in the full text of our paper. Now I will wrap up by talking about our future directions. As future works in this domain, we aim to identify tree species. However, more generally, we aim to extend our approach to go beyond trees to other hard-to-count and hard-to-localize objects, such as crowds, animals, biological cells, etc. We thank you very much for your time and attention.